Okay, so getting started, we're going to go through some definitions. You might have seen some of this in physics before. There are two main approaches for dynamic problems, and that is kinematics. The other approach is kinetics. They sound similar, but they're quite different. Kinematics uses calculus relationships to look at accelerations, velocities, so that the relationships between time, position, velocity, and acceleration. Versus kinetics, you're going to look at the forces acting on a system. So you're going to create free body diagrams, add up the forces in the x direction and the y direction. Just like statics, only unlike statics, the forces do not add to zero. The forces are not balanced. Because they are not balanced, they create motion. So the MA is the motion that the unbalanced forces create. And the acceleration here that you can get from the forces, that's the same acceleration that you can also get to through these calculus relationships. So it's the same acceleration either way. It's just a different way to get to what is happening here. Quick definitions, and I know you know this, but let's just take it the next step. We'll start with what we know and then build on what we know through this. Position. What kind of position measurements do we have? So one-dimensional systems where all you're worried about is linear motion. So we'll start out with what's called rectilinear problems, and this is something that is just moving in a straight line. It could go horizontal motion or vertical motion, throw a ball straight up in the air and have it fall straight back down. But everything that we can do is described by just kind of one degree of freedom, one plane where everything is motion. So that's 1D rectilinear motion. What's different from linear motion? What would cause us to have to use two coordinates to describe something versus just one coordinate? Well, it would have to be something that's curved, right? So curved versus linear. If it's following a curved path, which is like projectile motion, throw a ball in the air and watch it follow that kind of parabolic trajectory. So curved paths are going to require more than just a 1D description. So these are where you're keeping track of what's going on in the x direction, and then you have to keep track of what's going on in the y direction. And your velocities, accelerations, positions, it's similar to forces. So if you remember splitting forces into their x and y components, we're going to be splitting all of these vectors into their x and y components. So that will be curvilinear motion. And of course, you can also expand this into 3 dimensions too. A lot of motion can be smushed onto a 2D plane. So if you just orient your coordinate system correctly, then you won't have to worry about anything in the third dimension. But if you have a really crazy system that is actually, it's not moving in a plane, there is actually 3-dimensional coordinates for the motion. This is actually, you don't get into this until chapter 18, and it involves quite a few matrix analysis, but if you can do unit vectors and break things into XYZ components, this is what it turns into. Okay, so 1D rectilinear, 2D curvilinear, and curvilinear could be either 2D or 3D. We won't do too much 3D, so most motion you can fit that into a 2D plane. Okay, going from defining positions to defining a velocity. So hopefully you remember the definition of velocity from physics. Velocity is change in position over change in time. And if you're looking at a one-dimensional system, so rectilinear, moving back and forth on just a single straight line, so you would have some initial position that happens at time t1, and then at time t2 we're at a different position, and the new position is just a straight line in front of the old one. So you have some change in that position, and it took time for that change to happen. So that would be the one-dimensional velocity going on. If you have two-dimensional or three-dimensional motions going on, then we're going to get into vectors for this. Okay, so you have some initial position, and that position has some initial x, y coordinates, x1, y1, and then you have a second position that has some secondary coordinates x2, y2, and to go from one position to another position, you have changes happening in both the x and the y directions. So you're going to just compare the difference in those x coordinates, the difference in the y coordinates, and its vectors. So everything you did with forces in statics to split things into x and y components, it's the same thing with velocities and accelerations. So you'll have velocity in the x direction, and this velocity is influenced by the force that happened in the x direction. And then you'll also have a whole nother problem of what's happening in the y direction. So maybe you have gravity acting in the y direction that's changing that velocity around. And you're going to look at each of these individual components as you walk through your system. Same thing with the third dimension, okay? So if you can break things into x, y components, you can look at x, y, z components, and forces in the z direction will influence the accelerations and velocities in the z direction, as well as y and x. So it's interesting. It's actually independent systems. If you go 90 degrees from anything, and you can orient your coordinate system however you want, but anything that's 90 degrees away it's like a whole new universe out there, that what happens in the x direction stays in the x direction, forces, velocities, acceleration, and nothing in the x direction will influence anything in the y direction. So what's happening in the y direction, that's a whole nother world and a whole nother problem to figure out. Okay, position, velocity, acceleration. So acceleration is kind of the last one. And if you remember what acceleration is a change in velocity. So we're not looking at change in position anymore, we're looking at how the velocity is changing. So start out with a 1D rectilinear system again. Let's say we have a vehicle and it starts going 30 miles per hour and then it goes 60 miles per hour. It does not change direction. It's headed east in both scenarios, so it hasn't made a left turn or a right turn. The direction is the change, it's just the magnitude, okay? So this would be a 1D case where you're just looking at the magnitude of something changing in the x direction. And in that case, you can look at the vectors of it again. So we have v2 minus v1. So we're going to flip around v1, make it negative, and you can see the difference in these vectors when you add v2 and v1. There is our change in velocity, and that's what would go into our acceleration, and it took some time for that velocity to change. So 1D versus 2D. So 2D, we're going to have a velocity that might have two different directions, okay? So part of this velocity is in the x direction, part of this velocity is in the y direction. So now we have to keep track of things happening in both the x and y directions. Now these are just vectors again. So if we want to see how these velocities have changed, okay, so once again we're going to take v2 minus v1. To subtract a vector, you just flip the direction of that arrow. So now instead of pointing to the right, we're pointing backwards to the left. So v2 minus v1, and if you look at the difference between those vectors, here's v2 minus v1, that is where the acceleration was happening in. If you prefer to break everything into components instead of using the geometry in a more graphical method, that is fine too. So we can split up the starting and the finishing velocity. So here's v2 and we have two components to that, and here's v1, we have two components to that. Add everything together, and our change in velocity, it'll have x and y components for that too. So you can add those components together, just kind of similar to adding the forces in the x direction together or the forces in the y direction. You're just splitting everything into x and y components and adding all those vectors together. Okay, another little note about acceleration. Sometimes you think of acceleration like you would think of in your car. So you speed your car up or you slow your car down. Acceleration is not change in speed. So what's the difference between speed and velocity? Velocity is a vector. It has a magnitude and a direction. Speed is not a vector. Speed only has a magnitude. And so for acceleration, you're worried about more than just the magnitude. You also have to worry about the direction of the thing. So the best way to think about acceleration is not change in speed. The best way to think about it is what forces are not balanced in my system. If you can visualize what forces are not balanced, that tells you what direction and the magnitude of the acceleration that's happening. And so it's not change in speed, it's you're looking at the unbalanced forces is how to figure out what's happening acceleration-wise. Okay, once again, if you start thinking about forces, that's kinetics. But really jump into kinetics right away, because you should always be thinking about unbalanced forces and what's creating that acceleration. Why is it going in the direction it's going in? What magnitude is it? There's a force that created that motion for all of our cases. Okay, so here we have, let's call position x, velocity, change in position over change in time, acceleration, change in velocity over change in time. From physics, let's say we have a constant acceleration. So this would be like acceleration equals 9.81 meters per second squared, or 32.2 feet per second squared, or something. If acceleration is just a number, just some constant value that is not changing with time, so not acceleration from, internal combustion engine, that force is changing with time or something, but just some natural acceleration that's constant. Then we can take this a dv dt, we're going to rearrange this guy, pull the dt up to a dt equals dv, and if this is constant, right, we can go through a little integration here. So let's integrate from 0 to some time, initial velocity to a final velocity, and we get acceleration times time is equal to v minus v naught. Usually they write this equation as v equals v naught plus at. Okay, so you've seen this equation before. Just really remember this equation only applies where acceleration of your object is constant. Okay, another way to write this equation, and I guess some different countries use different nomenclatures or something. So when I write v parenthesis t, that's not velocity times time. This is just saying I have some equation and it's dependent on time in here. So these two equations are the same thing. It's just saying velocity is a function of time here. So I'm not multiplying by time. Okay, so now we have velocity is change in position over change in time. So rearrange this, v dt equals dx. Well, what's my velocity? My velocity is this v naught plus at. There's a time in that velocity. So I'm going to plug this velocity equation in here to just our standard velocity definition. So our equation dt, we're going to integrate with respect to time. So we're just plugging an equation in here. Okay, so instead of just v, this is now an entire equation over here that we're plugging in. So go through this integration and we get vt plus 1/2 at squared. See, the at goes to 1/2 at squared equals x minus x naught. So here's another equation that you're probably familiar with from physics. Okay, so x equals x naught plus v naught t equals 1/2 at squared. And hopefully you should probably have these equations memorized by the end of physics. Just remember, these are all derived from a constant acceleration. Now, going through this derivation, we did this for a is constant. What if a is not constant? What if instead of just a number here, we had some equation for how acceleration is changing with time, how fast you're speeding your car up, how fast that motor speed is changing or something? The principles here are all the same, whether it's constant or there's an equation. The only difference is when you pop up here and start integrating stuff, we're not going to start with this at equals v minus v naught. There's going to be some equation here that we have to integrate. So here's an example of where acceleration is not constant. So we have an equation down here instead of a number. Now we can walk from acceleration up to velocity to position, or from position to velocity to acceleration. Let's do the bottom up first. So let's say we know the acceleration of the object and we want to solve for what the velocity is or what the position is. So we know this, we want to find what's going on up here. Okay, so to go from acceleration to velocity, we're just going to use this a equals dv dt, or a dt is equal to dv. And instead of plugging in a number here, you take the whole equation and you plug the equation in. You have to know the limits of your integration, so what time, what's your initial velocity is very important. So boundary conditions come into play when you're dealing with integrations. So here we go from acceleration to velocity, and if we want to go from velocity to position, it's another integration. So velocity is equal to dx dt, or v dt is equal to dx. Once again, we're going to take this equation that we have and plug it in, and we're going to have to know boundary conditions. What is the starting position? What's the ending position? So if we know that, let's say we start at a position of 10 meters or something. So you plug that in, and we're going to get what our position is doing with time. So if you want to go from acceleration up, it's going to be some integration going on. Let's say we start with position, and we want to go from position and figure out then what velocity is and what acceleration is. Well, it's just going the other way, okay? So v is equal to dx dt, so we just take this equation and take the derivative with respect to time. So that's from position down to velocity. And then once we have velocity, acceleration is dv dt, so we're going to just take the derivative of that velocity with respect to time, and voila, you can get the acceleration. So you can go around this loop either way. If you have one of these three information, you can get the other two pieces, whether you start in the middle or the top or the bottom. It's just calculus to work your way around from one side to the other of it. One more thing I would suggest for everybody is to use some sort of math software. I'll be doing a bunch of stuff in Mathematica, but maybe use MATLAB or some of the free online sites. It doesn't matter what you use. Save it as a PDF, and then when it comes time for the test, I'll let you use math software for the test too, but you'll need to let me know kind of what you're using so I make sure that's loaded at the testing centers, and whatever testing center you're using, you'll have to contact them and make sure what software they happen to have loaded there. Or if you have some stuff on your calculator that solves this on your calculator, that's great too. But I don't want this to be a calculus class, it's the dynamics. So, but find something to do the calculus. This is what this sort of a thing would look like on Mathematica. So you have input, you define your function as a function of time, and to take the derivatives, it's as simple as this. So here's from our first output, this would be the velocity, and the second output comes from the second line, acceleration. First line was suppressed because of the semicolon. So, but whatever you use, probably use something. You can do it by hand if you want to, but it's better to use something. So graphing this stuff out is where you really start visualizing how the system is moving around. So just like you draw a free body diagram in statics to visualize the forces, you're going to use a graph in dynamics to visualize the motion. So let's start and look at initially what the position looks like. So here's plotting this equation. The position is a function of time. We have time on the x-axis and position. So we're still talking about rectilinear motion here. This is straight line motion, just straight up and down, a single path. Okay, and if you have position versus time, the slope of this curve, dx dt, is your velocity. So as you watch this position change, and you see this slope get steeper and steeper, that means our velocity is going up. So you should be able to start seeing multiple pieces of information in the same graph. Even though this is a graph of position, you can also see the velocity here. The velocity is the slope. Let's add in the velocity. Okay, so if we look at initially, the slope is actually going down to 0. It looks like the slope, it almost kind of flattens out here. It's not quite 0. So the slope is decreasing. It's getting shallower and shallower. And then from here on up, the slope is increasing. So even though the slope is positive all the way through, what's happening here, it's decreasing and then it's increasing. What does that mean with respect to acceleration? Another thing, when you look at velocity, velocity is related to kinetic energy, 1/2 mv squared. So if you're looking at a curve showing velocity, you're looking at the energy, the kinetic energy of the system. Velocity is also your angular momentum, your linear momentum, mv plus fdt equals mv. So it's more than just velocity you're looking at here. You're looking at energy of the system and the linear momentum of the system. Here's that last curve on there. So you notice that it gets straighter and straighter as we go from position is going to be the curviest curve, and then velocity and acceleration hopefully will get down to something that's linear or flat and not too weird looking. Okay, so acceleration is the slope of your velocity curve. You can see where acceleration goes to 0. That's kind of where that velocity is bottoming out. A lot of times they'll ask questions like, where is velocity the smallest? Well, to find where velocity is the smallest, you're going to go to where acceleration is 0. So acceleration will tell you information about your velocity curve, and velocity will tell you information about your position curve. So looking at these guys, and it's always interesting, the points that are interesting is where a minimum happens, where a maximum happens, and that's usually, you know, some spot where the slope goes to 0, and that slope is described, so the velocity slope is your acceleration, and the position slope is your velocity. But use some kind of software to graph it out, and then think through one time to the next how the energies are changing, the momentums are changing. Position, often that tells you potential energy, mgh, h is a position, or 1/2 kx squared, x is a position. So your position curve tells you potential energy, your velocity curve tells you kinetic energy, and then your acceleration tells you what unbalanced forces are happening in your system. So if you have a negative acceleration, there's a force pushing it in the negative direction here that's not balanced. Or if you have a positive acceleration, that means there's a force pushing in the positive direction that's not balanced here. So forces, kinetic energy, potential energy. It's more than position, velocity, acceleration. Okay, one more little thing to go through. So far, we have been doing everything with respect to time. What if we have acceleration as a function of position instead of time? Let's rearrange this a little bit. Okay, so A equals dv dt, dv dt. This is still dv dt. We're going to use a little chain rule here. You can multiply something by 1 and you haven't done anything. So we're throwing in some dx's, and what that does for us, dx over dt, this is velocity. So by replacing dx dt with velocity and getting acceleration in terms of velocity, we have gotten rid of time. So now we have acceleration as a function of position and velocity instead of as respect to time. And if you rearrange this guy, so v dv equals a dx. So now if you have some equation where acceleration is a function of position instead of time, this is the relationship that you can use to walk through it. Okay, so kinematic relationships integrate. So if we have something as a function of time, that's something that's a function of position, or you could even look at something as a function of velocity. What are we going to do with that? Okay, so time, this is a standard dv dt. We're going to integrate acceleration of time dt equals dv as a function of position. So this is where we're going to rearrange things and get everything in terms of velocity instead. And it's the same kind of principle, only now we have v dv equals some equation where acceleration is a function of position dx. Okay, so we can integrate an equation where acceleration is given as a function of position versus a function of time. And if you want something with velocity in there instead. These tend to be pretty nasty to integrate because you have that big old equation as the denominator in your fraction. So sometimes this requires a numerical or graphical solution rather than an analytic solution to solve these guys. And it's another reason where starting with a graph can be very helpful for these ones. So if you can't crank through the calculus, graph it out, and you can see the slopes changing and areas under curves on the graph.